Hello, my name is Jaydeep Sai, and the topic given to me is concept of interpreter. Interpreter computing. In computer science, an interpreter is a computer program that directly executes instructions written in a programming or scripting language without requiring them previously to have been compiled into a machine language program. An interpreter generally uses one of the following strategies for program execution: parse the source code and perform its behavior directly, translate source code into some efficient intermediate representation or object code and immediately execute that. Explicitly execute stored precompiled by the code made by a compiler and matched with the interpreter virtual machine. Early versions of Lisp programming language and mini computer and microcomputer based dialect would be examples of the first type. Perl, Raku, Python, MATLAB, and Ruby are examples of the second, while UCSD Pascal is an example of the third type. Source programs are compiled ahead of time and stored as machine-independent code, which is then linked at runtime and executed by an interpreter or compiler. For JIT systems, some systems, such as Smalltalk and contemporary versions of Basic and Java, may also combine 2 and 3. Interpreters of various types have also been constructed for many languages traditionally associated with compilation, such as ALGOL, Fortran, COBOL, C, and C++. General operation. An interpreter usually consists of a set of known commands it can execute and a list of these commands in the order or a programmer wishes to execute them. Each command, also known as an instruction, contains the data the programmer wants to mutate and the information on how to mutate the data. For example, an interpreter might read add Wikipedia users file and interpret it as a request to add file to the Wikipedia users variable. So an interpreter consists of a set of known commands it can execute. So the interpreter will consist of a set of commands which it can execute and a list of these commands in the order of programmer wish. So by the wishes of the programmer, how he gives the code, the interpreter will consist and it will store the programs. Each command, also known as an instruction, contains the data the programmer wants to mutate. So the data which the programmer wants to mutate is given to the interpreter and it will store the data and it will mutate the data. For example, an interpreter might read add Wikipedia users file and interpret it as a request to add file to the Wikipedia user variable. Interpreter have a wide variety of instructions which are specialized to perform different tasks, but you will commonly find interpreter instructions for basic mathematical operations, branching, and memory management, making most interpreters turning complete. Many interpreters are also closely integrated with a garbage collector and debugger. So interpreter have a wide variety of the instructions which are specialized to perform different tasks. So the interpreter has the wide variety of instructions for the performance of the different tasks. Wide variety of the tasks are performed by the interpreter, but commonly find interpreter instructions for basic mathematical operations. So the interpreter is also used for the basic mathematical operations and also for the branching and memory management, making most of the interpreters turning completely. Many interpreters are also closely integrated with a garbage collector and debugger. So the many of the interpreters are also closely integrated with the garbage collectors and debuggers. compilers versus interpreters. So we have learned about the interpreters. Now we will find the difference between the compilers and the interpreters. Programs written in a high-level languages are either directly executed by some kind of interpreter or converted into machine code by a compiler and assembler and linker for the CPU to execute. So the programs which are written in a high-level language are either directly executed by some of the kind of the interpreters or converted into machine code. So the programs which are written in the high-level programming languages are directly executed by some kind of the interpreters. So the some of the kind of the interpreters will execute the programs or it will converted into machine code by compiler. So the compiler will compile the code into machine code and assemblers and linkers. So the not only compilers, the assemblers and linkers will also try to convert the machine code, the code which is given to the program, and it will convert into machine code for the CPU to execute. So it will convert for the CPU to execute, while the compilers and assemblers generally produce machine code directly executable by computer hardware. So the compilers generally produce machine code directly executable by computer hardware. Then they can optionally produce an intermediate form called object code. This is basically the same machine specific code but augmented with a symbol table with names and tags to make executed blocks or modules identifiable and relocatable. While interpretation and compilation are the two main means by which programming language are implemented, they are not mutually exclusive, as most interpreting systems also perform some translation work, just like compilers. The terms integrated language or compiled language significantly that the canonical implementation of that language is an interpreter or a compiler, respectively. A high-level language is ideally an abstraction independent of particular implementations. So while the interpretation and compilation are the two main means by which programming language are implemented. So the mainly the programming languages are implemented by the using of the interpreters and compilers. So they are not mutually exclusive. So the interpreter and compiler are not mutually exclusive, as the most of the interpretation system also perform some translation work. So most of the interpretation system also work for the translation work, just like compilers. So like the compilers, the interpretation systems also perform some of the translation works. The terms integrated language or compiled language signifies that the canonical implementation of that language is an interpreter or compiler, respectively. A high-level language is ideally an abstraction independent of particular implementations. History of the interpreter. Interpreters were used as early as 1952 to ease the programming within the limitations of computers at the time. Example, shortage of programs storage space or no native support for floating numbers, floating point numbers. Interpreters were also used to translate between low-level machine languages, allowing code to be written for machines that were still under construction and tested on computers that already existed. The first interpreted high-level language was Lisp. Lisp was very first implemented in 1958 by Steve Russell on an IBM 704 computer. Russell had read John McCarthy's paper and realized to McCarthy's surprise that the Lisp eval function could be implemented in a machine code. The result was a working Lisp interpreter which could be used to run Lisp programs or more properly evaluates Lisp expressions. So we have studying the history of the interpreter. Interpreters were used in early as 1952. From 1952 onwards, the interpreters are being used to make the programming very easy within the limitations of the computer at that time. So when we see the example, a shortage of the program storage space or no native support for floating point numbers. So there is a shortage of the program storage space. So no native support for floating point numbers. So the interpreters were also used to translate between low-level machine language, allowing code to be written for machines that were still under construction and tested on computers that already existed. So the interpreters are used to translate the low-level language into high-level language. The first interpreted high-level language was Lisp. So the first interpreted high-level language was Lisp. Lisp was first implemented in 1958. So the Lisp was firstly implemented in 1958 by Steve Russell on an IBM 40704 computer. Russell had read John McCarthy paper and realized to McCarthy's surprise that the Lisp eval function could be implemented in machine code. So the result was working Lisp interpreter which could be used to run Lisp programs or more properly evaluates Lisp expressions. Compiled programs will typically use building blocks functions kept in a library of such object code modules. Linker is used to combine pre-made libraries files with the object file of the application or to form a single executable file. The object files that are used to generate an executable file are thus often produced at different times and sometimes even by different languages capable of generating the same object format. A simple interpreter written in a low-level language, example assembly, may have similar machine code blocks implementation functions of the high-level language stored and executed when a function's entry in a look up table points to that code. However, an interpreter written in a high-level language typically uses another approach, such as generating and then walking a parse tree, or by generating and executing intermediate software-defined instructions or both. So a simple interpreter written in a low-level language, example assembly, may have similar machine code blocks implementing functions to high-level language stored and executing when a function's entry in a lookup table points to that code. However, an interpreter written in a high-level language typically uses another approach such as generating and then walking a parse tree, or by generating and executing intermediate software-defined instructions or both. Thus, both compilers and interpreters generally turn source code, that is, textile files, into tokens. Both may or may not generate a parse tree, and both may generate immediate instructions for a stack machine, quadruple code, or by other means. The basic difference is that a compiler system, including a built-in or separate linker, generates a stand-alone machine code program, while an interpreter system instead performs the actions described by the high-level programming. So both the compiler and interpreters generally turn the source code. So they turn the source code into tokens. So generally the interpreter and the compilers turn the source code, which means text files into a token by generating a parse tree, and both may generate immediate instructions for a stack machine, quadruple code, or by other means. The basic difference is that a compiler system, including a built-in or separate linker, generates a stand-alone machine code program, while an interpreter system instead performs the action described by the high-level program. A compiler can thus make almost all the conversions from source code semantic or to the machine level ones and for all, that is, until the program has to be changed, while an interpreter has to do some of these conversions work every time a statement or function is executed. However, in an efficient interpreter, such of the translation work, including analysis of types and similar, is factored out and done only the first time a program, module, function, or even statement is run, thus quite akin to how a compiler works. However, a compiled program still runs much faster under most circumstances, in, in part because compilers are designed to optimize code and may be given ample time for this. This is especially true for simpler high-level languages without many dynamic data structures checks or type checking. Traditional compilation, the executable output of the linkers .exe file or .dll files or a library. C picture is typically relocatable when run under a general operation system, much like the object code modules are, but the difference that this relocation is done dynamically at runtime. That is, when the program is loaded for execution. On the other hand, the compiled and linked programs for small embedded systems are typically statically allocated, often hard-coded in a NOR flash memory, as there is often no secondary storage and no operation system in this sense. Historically, most interpreter systems have had a self-contained editor built in. This is becoming more common also for compilers than often called an IDE, although some programmers prefer to use an editor of their choice and run the compiler, linker, and other tools manually. Historically, compilers predate interpreters because hardware at that time could not support both the interpreter and interpreted code, and the typical back environment of the time limited the advantages of interpretation. Development cycle. During the software development cycle, programmers may frequent changes to source code. When using a compiler, each time a change is made to the source code, they must wait for the compiler to translate the altered source files and link all of the binary codes files together before the program can be executed. The larger the program, the longer the wait. By contract, the programming using an interpreter does a lot less waiting, as the interpreter usually just needs to translate the code being worked on to an intermediate representation or not translate it at all, thus requiring much less time before the changes can be tested. Effects are evident upon saving the source code and reloading the program. Compiled code is generally less readily debugged and edited. Compiling and linking are sequentially processes that have to be conducted in the proper sequence with a proper set of commands. For this reason, many compilers also have an executive aid known as a makefile and program. The makefile lists compiler and linker commands lines and the program source code files, but might take a simple command line menu input. Example, make 3. It selects the third group set of instructions, then issues the commands to the compiler and linker feeding the specified source code files. Distribution. Compiler converts source code into binary instruction for a specific processor architecture, thus making it less portable. This conversion is made just once on the developer's environment, and after that the same binary can be distributed to the user's machine where it can be executed without further translation. A cross compiler can generate binary code for the user machine even if it has a different processor than the machine where the code is compiled. An interpreted program can be distributed as source code. It needs to be translated by in each final machine. which takes more time but makes the program distribution independent of the machine's architecture. However, the probability of integrated source code is dependent on the target machine actually having a suitable interpreter. If the interpreter needs to be supplied along with the source, the overall installation process is more complex than delivery of the monolithic executable, since the interpreter itself is a part of the what need to be installed. The fact that the interpreter code can easily be read and copied by humans can be of concern from the point of the view of copyright. However, various systems of encryption and obfuscation, etc., exist. Delivery of intermediate code such as bytecode have a small effect to obfuscation, but bytecode could be decoded with a decompiler or disassembler. Efficiency. The main disadvantage of interpreter is that an interpreted program typically runs slower than if it had been compiled. The difference is speeds could be tiny or great, often an order of magnitude and sometimes more. It generally takes longer to run an program under an interpreter than to run the compiled code, but it takes less time to interpret it than the total time required to compile and run it. This is especially important when prototyping and testing code, when an edit internet debug cycle can often be much shorter than an edit compile run debugging cycle. Interpreting code is slower than running the compiled code because the interpreter must analyze each statement in the program each time is executed and then perform the desired action, whereas the compiled code just performs the action within a fixed content determined by the compilation. This runtime analysis is known as interpretative overhead. Access to variables is also slower in an interpreter because the mapping of identifiers to storage location must be done repeatedly at runtime rather than at compile time. There are various compromises between the development speed when using an interpreter and the execution speed when using a compiler. Some systems, such as some Lisps allow interpreted and compiled code to call each other and to share variables. This means that once a routine has been tested and debugged under the interpreter, it can be compiled and thus benefit from faster execution while other routines are being developed. Many interpreters do not execute the source code as it stands but convert it into some more compact internal form. An interpreter might well use the same lexical analyzers and parsers as the compiler and then interpret the resulting abstract syntax tree, example data type definitions for the letter, and the toy interpreter for syntax tree obtained from C expressions are shown in the box. Regression. Interpretation cannot be used as the sole method of execution, even though an interpreter can itself be interpreted, and so on. A directly executed program is needed somewhere at the bottom of the stack because the code being interpreted is not by definition the same as the machine code that the CPU can execute. Bytecode interpreters. There is a spectrum of possibilities between interpreting and compiling depending on the amount of analysis performed before the program is executed. For example, the Mac list is compiled to bytecode, which is a highly compressed and optimized representation of the Lisp source, but it not machine code and therefore not tied to any particular hardware. This compiled code is then interpreted by a byte type interpreter itself written in C. The compiled code is in this case is a machine code for a virtual machine, which is implemented not in hardware but the bytecode interpreter. Such compiled interpreters are sometimes also called comparators, threaded code interpreters. Threaded code interpreters are similarly to byte code interpreters, but instead of bytes, they use pointers. Each instruction is a word that points to a function or an instruction sequence, possibly followed by a parameter. The threaded code interpreter either loops fetching instructions and calling the functions they point to, or fetches the first instruction and jumps to it, and every instruction sequence ends with a fetch and jump to the next instruction. Abstract syntax tree interpreters. In the spectrum between interpreting and compiling, another approach is to transform the source code into an optimized abstract syntax tree, AST, then execute the program following this tree structure or use it to generate native code just in time. Template interpreter, making the distinction between compilers and interpreters yet again even more vague, is a special interpreter design known as a template interpreter rather than implement the execution of code by virtue of a large switch say, statement containing every possible byte code while operating on a software stack or a tree walk. A template interpreter maintains a large array of byte code or an efficient intermediate representation mapped directly to corresponding native machine instruction that can be executed on the host hardware as key value pairs, known as template. When the particular code segment is executed, the interpreter simply loads the opcode mapping in the template and directly runs it on the hardware. Self-interpreter. A self-interpreter is a programming language interpreter written in a programming language which can interpret itself. An example is a basic interpreter written in BASIC. Self-interpreters are related to self-hosting compilers. If no compiler exists for the language to be interpreted, creating a self-interpreter requires the implementation of the language in a host language, which may be another programming language or similar. By having a first interpreter such as this, the system is bootstrapped and new versions of the interpreter can be developed in the language itself. I thank the faculty and the college for giving me this opportunity to speak on the interpreters. Thank you.